Correct.
Okay.
Welcome everyone to this week Autonomy Talks. This week is a great pleasure to have with us Professor Igor Gilitschenski. I hope I spelled it correctly.
Perfect.
Who is an assistant professor of computer science at the University of Toronto, where he leads the Toronto Intelligent Systems Lab, and he's also a part-time research scientist at TRI. So something about Igor. He obtained his diploma in mathematics from the University of Stuttgart, and he then got his PhD in computer science from Karlsruhe Institute of Technology. Then he spent a while here at ETH Zurich, where he worked on robotic perception and in particular localization and mapping. And he then moved to MIT, where he was a research scientist at CSAIL and in the distributed robotics lab. In general, his research interests involve developing novel robotic perception and decision-making methods for challenging dynamic environments. And as you can see in the bio, he won several awards for his interesting papers. Today, he's going to talk about interactive navigation for robust autonomy, mixing some prior work up to the ETH days, coming from things he's doing today. And we are all very excited about this talk. So I'll let you the stage, Igor. Go ahead.
Yeah. Thanks so much. Thanks so much for the invitation and for the super kind introduction. I'm a roboticist, as you've heard from this introduction, only in my third career. So I started with mathematics, and my PhD was on state estimation, and then it was, I think, a coincidence that I got hired at ETH. I was lucky because I think Apple hired away a lot of Roland's postdocs. And I came, and coming from state estimation, I believed I know all about sensor fusion. But if your sensor fusion have to work on an actual robot, it's like a whole different ball game, and you have to consider so many things. So yeah, joining robotics was for me a big change. And in this time, since I started working on robotics, I was very lucky. I got exposed to a big variety of different types of platforms where robotics algorithms got deployed. So I want to briefly show some of those platforms. They were just very exciting. So one of the platforms that we've been working on, the first one was, the first one that I show is this one. It's like a very weird looking drone. And the amazing thing, and that was something that about which I was very excited in my time at ETH, is this drone that you see here was completely built and designed by undergrad students. I was the main project supervisor, and it was one of ETH's focus projects. So I assume many of in the audience here are from ETH. For those who aren't, these focus projects were an amazing opportunity for some students in their last year of bachelor studies, where they form a group of like 9 people and work intensively on one particular design project. And here the group worked on a drone that has tiltable rotors. And the amazing thing about this drone is that it could fly in any orientational configuration. So our motivation initially for working on it was to see if we can design a system that can be useful for aerial inspection, for contact-based inspection. And there is now a variant of this drone that is also developed in a startup that has the same name as the initial focus project, Voliro. They slightly modified the design, but the key idea of having tiltable rotors and allowing contact-based inspection is still there. Another robot we worked on at ETH were autonomous planes. This is the Atlantic Solar platform that was involved in multiple perception and also decision-making algorithms for autonomous planes, such as detecting landing sites or flying in strong wind fields. And there were a lot of amazing people working on these projects, and I think they continue some of this work to this day. One platform that is not a robot at all is Google VR headset. We worked a lot on localization and mapping in ETH. This VR headset was back then part of Google's Tango project. They restructured it slightly, but a lot of actually robotics algorithms that were developed by roboticists found later their main use case on mobile platforms such as smartphones and VR headsets. that don't involve any actuation. And when I moved to MIT, there was mainly one robot I worked on. And some people might say it is the most boring robot because there is no actuation. It's not flying. We didn't even build it ourselves from scratch, but we did the retrofitting from scratch. And this robot was an autonomous car. And what makes this boring robot so exciting is that this seemingly boring robot operates in the most exciting of all environments. So the big challenge with autonomous driving that we've worked on is not necessarily building a new robotic platform or optimizing some characteristics, the technical hardware characteristics of this platform. The big challenge of autonomous driving is making it work in really complex environments where humans do all types of crazy things. And multiple people, including Emilio, have dedicated their large chunks of their career to solving this big problem. And a lot of my work in the past years has been on autonomous driving. So I want to, in this talk, to talk about some of the interesting problems related to it. So when we think about autonomous driving, I grew up with this TV show. We think about a car that has very dry humor and its driver who believes that the Berlin Wall fell down because of him. And we imagine that there is this is to be super intelligent, and that's kind of what we hope for to design. But the reality of autonomous driving is that even simple systems such as parking sometimes fail due to sensor failure or some errors in the algorithm. And these failures in parking cases are annoying and costly. In cases where we have high-speed driving involved, such failures might actually be risky to lives, and avoiding these failures in all types of cases and all types of scenarios is like the big challenge of autonomous driving. Now, these days, in autonomous driving, we have a big groups and big companies doing research on that. So one question to ask is, what are the research challenges for universities? What is the next thing? One thing that we thought of as one of the important research challenges is overcoming the more principled limitations of autonomy stacks. So if you think about a traditional autonomy stack relies on centimeter level localization. So typically we have vehicles driving and localizing in some sort of very detailed 3D map, which also may know as HD maps. And these vehicles, they basically at any given point in time try to know where precisely they are in a detailed 3D map. And a system like this, if you look at the scenario that I'm showing here, can easily fail. And there are many different reasons why this fails. In this particular case, there are two that stand out. One is perceptual aliasing. So no matter where the vehicle is, this is potentially even for a human difficult. It's very hard to say for a vehicle whether it is or for a human, whether it stands in one location of the road or for 50 to 100 meters further down the road. It just all looks so similar. And even if a vehicle has a very good 3D model that allows the vehicle to model all the trunks of the trees and whatever, the vehicle has to cope with a different challenge, that this road might look completely different a few months from the time at which this picture was recorded. So classical HD maps that rely on highly detailed localization in a setting like here may potentially fail, and we need to think about how to drive without relying on them. And actually what humans do is humans don't have at any given time during the driving task, they don't have a perfect 3D map of the environment. We just roughly know where the road is, we can segment the road, and we just follow it. And we only rely on a high-level topometric map in our head. So the goal that we had is to ask, why do we need to localize at a centimeter level at all? It should be perfectly sufficient if we if we localize roughly, if we roughly know at which road segment we are, and we only need somewhat precise localization once we are at an intersection. And that's exactly what we did. We took our classical driving pipeline that we had for our vehicle, and we modified a few components in this pipeline. One component that we took away is the classical centimeter level localization that we had, and we replaced this localization by a segmentation and map warping module. And we also modified the motion planner to account for that. So the topological map that we use is simply a map that comes like from OpenStreetMaps in our case. And the claim that we make is that this is actually better in some situations. It's better because it has a lower cost to create, and it has at the same time a longer lifetime. So in 3D maps, they may become easily outdated, not only in these driving scenarios in the countryside, but they can become outdated if you go to cities, and in cities if there is some construction going on. So having fully detailed 3D maps is somewhat difficult to maintain. It comes with high cost, high storage size, and we wanted to get rid of this all by simply using an existing map. And we connect this map to the driving scenario by simply segmenting out the road. In our case, we used it was some early work. We used some very simple LiDAR-based segmentation and a relatively simple classifier. There are now much more complex papers that do this task. And we basically align the segmented road with our internal map representation. And then we have simply an optimization-based motion planner that allows us to optimize for trajectories to stay on the segmented part of the road. And here in this video, you see the actual real-world experiments that we have done at our testing site in Devens, which was a testing site not far from MIT in a small town. And the nice thing about this driving scenario that you see here is that Teddy, who has been leading the project and sitting here in the car, he did not use any centimeter level localization. So we were purely driving based on our OpenStreetMap types map. So this idea, back when we started, it was one of the early ideas that works to consider this type of problem. By now, you will see a lot of companies following a similar path. So, for example, in Toyota, people talk about some variant of like dialable perception. You will see people in Tesla who also argue that they don't need fully detailed maps if they can recognize the road well enough. So road scene understanding became more and more important, and we also have some follow-up works to this that try to do road scene understanding in more complex driving and road scenery scenarios where you have multiple lanes and where you try to drive in like complex driving patterns with other vehicles. Let's look at another scenario where humans can drive and where autonomous vehicles so far are struggling. A scenario like this, where it is strongly snowing, this scenario is very hard for an autonomous vehicle for multiple reasons. To even like an idea like MapLight, where we don't rely on highly detailed maps, might fail here because in a very strong snow setting, it is very hard to recognize road boundaries. Here, it's not even clear where the road starts and ends, and it needs a very good detection system. At the same time, humans can drive here, and what humans would do, they do basically two things. They drive much slower than usual, and the reason why we as humans drive much slower is we need to be able to detect other objects, and the visibility range is limited. So to detect other objects, we drive slower. For humans are kind of good at detecting even very coarse cues for where the road is. So even this somewhat snowy road is fine with us. We would still be able to detect it. But for autonomous vehicles, this type of snowy road is typically very problematic. So here we would need actually some sort of precise localization, but we cannot use any of the traditional cues. So the traditional cues would be trees in the environment, would be some sort of differential GPS, which may not be available. So the classical GPS might not be, is not precise enough. So we cannot look in the environment around us. But we can do something different. We can look under the ground. And that's not what humans would do. We don't have this type of sensing modality. And this is also not what most current autonomous vehicle companies are doing yet. Some are supposedly doing this in secret. But we put this idea to our test, and the test that we had for this idea is by using a ground penetrating radar. So a ground penetrating radar is what its name promises. Instead of looking around the vehicle, the ground penetrating radar looks under the ground. And the interesting thing about the stone and the soil formation underground is that it is locally unique. So what does this mean? It means that if we look at a pattern nearby, it will look slightly different. The scans that our radar yields us nearby will always look slightly different. And in combination with GPS, where the GPS is used to get some sort of coarse pre-localization, a ground penetrating radar can actually be used to safely localize a vehicle with centimeter level precision. So here you see the ground penetrating radar that we used on our vehicle. It has been initially developed at Lincoln Labs at MIT and presented, I think, the very first prototype in 2015. And we basically built up on this prototype and integrated it with autonomous driving and integrated it with an autonomous driving stack. So this radar here has 11 arrays, and it basically looks at responses at different depths, from different depths. So let's see how the data looks like for one of these 11 arrays as we drive along a road. So this is the response of one of these 11 arrays, and we have, because we have 11 of these responses, we basically end up at any given point in time with a picture. I think that resolution in one dimension it's 11, and I think in the other dimension it's something like 300. So we end up with a somewhat untypical 11 by 300 pixels image, and we have to use this image as a unique fingerprint. We don't have to rely on one image. It's a streaming type of data, so we can rely on multiple images. And even a naive method such as scan matching, we started with the most naive method possible to validate the idea. So even a naive method such as scan matching has been successful in demonstrating that driving with ground penetrating radar is possible. So what you see here is driving on a snowy road. And what is interesting is that the underlying map that we used for some of the driving here has been recorded in a completely different season. So when the trees still had foliage, when there was no snow on the road, and still with this with the ground penetrating radar approach, we were able to successfully localize up to a centimeter level. We used a very simple scan matching method, and we used a simple particle filter for the estimation. So there is room for more, but it's also a very interesting research topic because the type of data is a little bit different from all the other data sources that we traditionally use in SLAM, even different from radar-based SLAM, because now we're looking underground and creating like these underground fingerprints. So we believe this is like a very exciting research topic if we really want to enable autonomous vehicles to drive in challenging weather conditions such as snowstorms. The problem with ground penetrating radar research is that ground penetrating radar research basically requires to have one of these radars. And to the best of our knowledge, there are now 2 companies working on ground penetrating radars. But even with these companies working on them and maybe selling prototypes, it's a relatively expensive sensor. So we released a ground penetrating radar data set that people can use for doing their own SLAM research. And I believe by now there is even a second data set released by colleagues from CMU. So we are reaching a critical mass where you can try out whether your SLAM ideas will actually work on this type of sensing modality and what needs to be changed for this type of sensing modality if you want your GPR to work. Okay, so let's take here a small cut on the navigation topic and think a little bit about the full autonomous vehicle stack. There are some big challenges with the deployment of autonomous vehicles, and one of the big challenges is safe learning and safe validation of the system. For the industry side, the validation is the more important part. Researchers are more interested in driving policy learning and seeing how far this can be pushed. Making this safe requires good simulators and requires simulators that are inherently realistic. So one of the ideas that we were looking at MIT was whether we can build so-called data-driven simulators. Let's quickly look at this problem from the viewpoint of driving policy learning. Our goal in driving policy learning is to have a deep learning based method where we learn a control method for steering the car from image input. And if we want to use this, for safe driving, even in difficult scenarios, we need a good data set. And this good data set ideally needs to contain dangerous or complex driving situations. And this requires a really good human driver that can safely drive in seemingly difficult driving situations and recover a vehicle. So in practice, this comes with all types of problems. The same thing is for validation of driving pipelines. If you want to validate a driving pipeline on complex driving scenarios, including complex perception, you would need to have some sort of data sets that can do this for you. And in practice, we don't have such data sets, and we also don't want to create them simply because it's dangerous. So the idea that we had, and this work explicitly focuses on the perception side of things, is can we use real-world data to build better simulators? And this would allow us for policy learning, would allow us to learn some sort of driving policy without any human supervision and to automatically generate real-world edge cases. So when working with simulation, there are several paradigms. One paradigm is to simply use some sort of model-based simulation. And model-based simulation in the broadest sense means that there is some sort of designer or engineer who writes down a model of how vehicles behave, of how they look like, and this 3D model is then transferred via classical graphic techniques into some sort of simulator. And the most popular types of such simulators are based on video game engines, and we simply used video games for this type of research. One prominent example is Carla, and by now there are more examples in other domains such as AirSim and so on. So these simulators, if you use them, they typically do not capture the semantic complexity of the scene, and they don't have photorealism. And in order to do any type of policy transfer from these simulators to real world, we typically need to use a lot of domain transfer techniques, which come with their own set of challenges. More recently, there has been the emergence of a new type of simulators, and this new type of simulators, by now you can see it for all areas for which we require simulation. Our work here focuses on perception, but there are variants focusing on dynamics learning and variants focusing on behavior learning. And this new type of simulators shares a unique characteristic. Instead of having some designer and some person with high-level knowledge design the full simulator, we try to use real-world data as far as possible in the simulator, and then based on the real-world data, build the simulator and only inject as little as possible prior knowledge where we basically don't have real world data, or where we believe that it will help us. So in our case, we wanted basically to have a photorealistic synthesis of new driving viewpoints. What does it mean? It means that we start with a data set that looks somewhat like this. This is just a data set that we recorded off of our vehicle. And we want to allow to perturb the viewpoints in a meaningful way. So we want to end up with a data set with new viewpoints that look like this. So we want to have small perturbations, and this small perturbations of the viewpoint will allow us to basically mimic the driving and mimic driving in any way we want in the simulator. At the same time, in contrast to these model-based approaches, this type of simulator allows us to stay photorealistic. So you see here basically perfect photorealism, or almost perfect photorealism. There are some deformation artifacts, but as we will see, the level of photorealism that we get in such simulators is good enough to safely learn driving policies for a reinforcement learning agent. So how does the pipeline of our simulator look like? So as mentioned, we start off with some data set, and this data set has basically consists of images. It can consist of depth maps, or we can estimate the depth, so images, depth maps, and locations at which each image was recorded. And then we have some sort of virtual agent location in this world. And based on this virtual agent locations and some agent dynamics model, which is in this case still handcrafted, but can also be replaced by a data-driven model, we obtain a new position which has not been observed in the data set. And what we can do once we have obtained this new position is we can basically create a local 3D reconstruction of our image, and we can transform this 3D reconstruction such that it mimics the location, the viewpoint of the agent in this virtual setting. And then from this transformed observation, we can perform interpolation and obtain a new image. And as long as the agent does not deviate too much, the new image is more than we need for perfect learning of a driving policy. And we tried this out with a reinforcement learning approach. And the interesting thing about our approach, we used a very simple cost function. And back then we even used a very simple reinforcement learning algorithm. So we literally just used vanilla policy gradient, and we didn't even use any of the variance reduction tricks. Because for us, it was one of our first reinforcement learning projects. So we really just tried to do all of this on a very simple policy learning approach. And the interesting thing is we ended up with with stable driving in real world. So we had zero-shot deployment to the real world. The thing that is amazing about this is that this vehicle's driving policy, although a deep neural network, has actually never seen a human driving command. So it has been purely trained in reinforcement learning. And to the best of our knowledge at the time when we released this work, this has been the first work that had a car that has been purely trained in reinforcement learning and simulation be transferred to the real world and could drive without any form of fine-tuning. So the big advantage of these data-driven simulation approaches is that this inherent photorealism allows us to reduce this sim-to-real domain gap and not worry too much about complicated domain transfer techniques. We compared it with some other traditional approaches, such as domain randomization, domain adaptation, or purely imitation learning. And the interesting thing is that with the same using the same amount of data, our approach was more efficient in the sense that less interventions, human interventions were required for the car to drive safely, and it also better reproduced the trajectory that would go along the center line. So we ended up with a very efficient trajectory. Another interesting result is that our approach was also more more efficient at recovering from weird initial positions, some of which were not even observed in the data set. But because we had this reinforcement learning-based training and the agent was able to explore during training time, it was safely able to recover. Again, this policy learning approach is currently maybe more interesting on the research side, although there are some AV companies looking into policy learning for their stacks as well. But the big value of data-driven simulation that you can have already even for classical driving stacks is, of course, that it gives you a realistic way to handle, to check for perception while also incorporating control in the loop. And by now it's like a huge topic at U of T. Raquel's group has also done a lot of work on data-driven simulation, and it kept us excited until today. So our most recent work extends our prior work, where by also incorporating new sensors. Initially, we only simulated cameras. Now, in the new version, we also added 3D lidars and an event camera. Event cameras were something about which I actually learned when I was in Zurich and attended a talk by Davides Karamutsa. And it's a very exciting sensor also for the driving task. So for us, it was an opportunity to add it to our simulator as well. And by now you can download the simulator, check it out, and play around with it yourself. I hope you will get around to organizing a challenge with it at some point, and maybe even deploying winning algorithms on a car. But this is so far in the planning. One of the big challenges now with these type of simulations is making them editable, and a lot of the research in my current group goes in the direction how to make them editable, how to make them useful for other robotic tasks such as manipulation. So for example, one of my first generation graduate students has worked on neural radiance fields and on making reconstructions from neural radiance fields editable. And here his contribution was in the work that we'll present at ECCV. He presented an idea where you can very simply take some scene and create reconstructions that don't contain certain objects you don't want it to contain. So for example, here you have an input image that contains a plate with a hot dog, but you want a reconstruction only of an empty plate. So in our work, we combine very sparse annotations that are only required at some parts of the image with CLIP, which is like a neural network model that combines image and text input into a joint representation space. And we use this to inform the training of our neural radiance field. And this allows us to obtain 3D reconstructions of an object without some of the objects that were occluding parts of it. On the driving side, we have also extended Vista to dealing with multiple agents, which we also presented at this year's ICRA. And this allows us to evaluate more complex driving scenarios where agents behave adversarially to each other, and to develop also more complex driving policies. So we evaluated it on different maneuvers, for example, avoiding a car and to recovering to a lane, or making a challenging turn where the road where the road curvature is at the same time as you try to overtake another vehicle. And it is also has been useful in analyzing failure cases. So for example, if you use learning-based driving policies and you drive long enough next to another vehicle, you may end up with actually not forgetting about the vehicle being there and accidentally crashing in it. So here our driver had to intervene to avoid an accident scenario. So it's a very data-driven simulation, gives very interesting insights into how to train driving policies or how to evaluate the autonomous vehicle driving stack. I want to come to the last big scope of topics for today, and this is inspired by learning-based control, and particularly in a multi-agent setting. And the limitations of autonomous driving or of driving we usually see at racing. So racing pushes everything to the limit. You might have adversarial perceptions due to direct sunlight. You have to run your vehicle at the limits of its controllability. And using learning-based control for racing, particularly in a multi-agent setting where the other agents may be adversarial, is a very big and open challenge. And we set out to address this challenge at first in simulation, and I hope at some point that's the ultimate vision, that we will have a learning-based agent outperform humans actually in a vehicle, in an actual vehicle race that is tire-to-tire race, not just at race time. And we were inspired by some of the success of self-play algorithms. So just as a reminder, self-play algorithms are basically neural network training techniques where an algorithm plays against copies of itself and that way this algorithm learns better variance in a competitive setting. And this has been used for a big variety of these big reinforcement learning success stories, such as AlphaStar. It has been used for poker and multiple settings. The approach that we presented slightly differs from these approaches in that we have a model-based self-play. So model-based self-play has a learned world model which allows agents to compete in imagined games and learn from limited observations. So what does it mean? It basically means that we try to mimic what a human is doing by imagining how the future behavior of opposing agents would be. So each agent has now the ability to not only reason about its own behavior, but also about other agents' behavior. So in our method, we basically use some form of high-dimensional pixel input. In our case, we used a modified version of OpenAI Jim's racing environment. And this input is encoded into a latent embedding. And this latent embedding is then used for learning a policy, for learning one-step rewards, and for learning a value function. And one of the challenges is to model the interactions between the different agents. So in our case, the world model is learned from rollouts, and these rollouts are stored in a data set of past experiences. And the latent embedding is learned by training the agent to reconstruct its own observations and to predict also the observations of its opponents from the latent state. And here you see the prediction of the opponent's observations. And the interesting thing is we do this prediction of the opponent's observations without having access to the view that the opponent has access to. So this allows our agents to learn reasoning about the opponent's behavior. At least this is our hope. So we hope if our agent is capable of reconstructing future observations of the opponent, it is also capable of knowing where the opponent will go. And here you see a nice example. Reconstructing the own state is, of course, always a much easier task for the agent than reconstructing the opponent's state. This is much noisier, which you can see here. But our agent still successfully learns to predict the opponent's state from its own latent space. Okay, and the rest of the story is relatively usual to model-based reinforcement learning. So we use the world model that we learned to derive behaviors and learn a value network. And in fact, our approach was very much based on the Dreamer agent. So we modified the Dreamer agent to be capable of this multi-agent model-based self-play. And using our two-agent world model basically allows for modeling the interactions during this entire process. And at test time, as mentioned, we do not have any access at all to the opponent's observations, and the agent's own observations are just used to predict the opponent's latent space and subsequently its actions. So let's look at some of the fun stuff at what we get. The agent is pretty fast at learning lane stable driving. So, which is like a very common observation that you also see in more recent racing papers. The driving task and staying in the lane is actually the easy task. But what is the much harder task and happens much later during training time is doing things such as aggressive overtaking or even forcing an opponent off the road. And towards the end, we happen to think that our agent even learned this pit maneuver where an agent is not just forced off the road, but also aggressively resulted into losing the stability of the other vehicle. And we would be, of course, super excited to see this thing go live on some real-world platform at some point. But you guys can imagine that doing this type of experiments, even with small-scale cars, is not that easy. They need to be super robust so we can allow for this type of cool crashes and cool behavior. So as we worked a lot with policy learning methods in RL, we noticed something that many RL practitioners noticed. And typically, if we have some sort of continuous control policy, and we evaluate this continuous control policy on some continuous control benchmarks. But what happens in practice is that agents often saturate within these continuous control spaces. They often saturate at the limits of what they are allowed to give. And this behavior, to everyone who does actual control theory, is actually familiar. It is known as bang-bang control. So instead of using like the entire range of possible control inputs, bang-bang control often arises in reinforcement learning agents. And until recently, there was not much literature analyzing this behavior and explaining it. And people did not know why this is happening. And again, someone who is familiar with optimal control will actually say, of course, bang-bang control is happening even in some continuous control tasks. For example, for certain types of control problems, such as minimum time control problems, or here max state or min fuel control problems. There are classes of control problems for which a bang-bang controller is actually the optimal controller, even if other control inputs are possible. And what is happening in the RL setting is that this behavior that we know from control theory is actually mimicked in the RL setting. So what we did is we evaluated the emergence of bang-bang controller in traditional control benchmarks. And to do this evaluation, we took a bunch of standard reinforcement learning algorithms, and we replaced their Gaussian policy head by a Bernoulli controller or by a bang-bang controller. What does it mean? So typically, policy reinforcement learning algorithms output some mean and maybe some variance. They output a Gaussian, and this Gaussian is used as a control input for your system. Sometimes just the mean is used and the variance is only relevant for training. Sometimes people sample from the outputted distribution. Basically, we changed this distribution assumption, and we simply enforce the bang-bang controller. And the motivation for this was relatively simple. We observed the Gaussian policy heads, and we realized that even if we don't replace the bang-bang controller, the system learns some form of bang-bang control, which you can see here, here in green. So the interesting thing is that Gaussian, even if when we use Gaussians as the control output or as the distribution output of our learned policy, we end up with bang-bang controllers, and we evaluated this. And the interesting insight is that using these bang-bang controllers yields actually often state-of-the-art results on traditional control benchmarks. And this has been an amazing insight because it kind of shows that the type of benchmarks that we have been currently using And the way these reward functions are structured in these benchmarks actually encourage often some sort of bang-bang behavior. And as a big learning takeaway from this, that has been also like an important learning takeaway from us, is that it is very important to think carefully about how we design the benchmarks, and also if we do reward shaping, how we shape reward functions in order to avoid bang-bang behavior, because it is usually mechanically not desired. No robotic system wants to go back and forth between the optimum of its, the extreme of its controls. And we are also looking into follow-up work on this. But for today, I want to end my talk, and I look forward to all of your questions. This, by the way, is a picture of the Mississauga campus of the University of Toronto. You should check it out and visit us anytime you are in Canada or in North America.
Thank you, Igor, for the talk. Let's open the stage for questions. You can either type the questions in the chat and I will read them for you, or raise your hand and I'll give you the word.
I have a question about this last idea of bang-bang control.
Yes.
And it's very fascinating, actually, when you realize you put priors in your problem that you didn't realize you put. Maybe like the reward or the model itself. I think also another source, and the question would be like, is this the problem here? Is that the way you write down the dynamics, right? For example, here, so I know that for a real self-driving car, bang-bang control is not the optimal strategy. Mm-hmm. When you think about brakes and acceleration, and I guess, how do you do the steering? That's a big question, right? So, yeah. So if you find bang-bang control in your simulation, is it a consequence of how you actually encode the control signals, or is it just something that's invariant of the parameterization of the controls?
Mm-hmm. So I think it is also related to the reward function. So for example, let's say even for a self-driving car, you can construct some reward that will encourage bang-bang controllers. Let's say you drive on a straight road and you want to go as fast as possible from A to B, and you want to stay at the position B, you want to come to a halt. Then your optimal control strategy, at least for most of the time, would be maximum acceleration up to a certain point and then maximum deceleration. So depending on how your system is parameterized for this type of control task, because it's a minimum time control problem, you will end up with a bang-bang controller. So this is one of the sources. But there are also other sources where you may end up with some sort of bang-bang or a bang-off-bang controller.
Yeah, but I mean, for again, like in your particular case for steering, like just trajectory following, typically what we say is that when you look at the linearized system, then it's well approximated by an LQR controller, right? And actually, mm-hmm. You make sure actually you're not in the, so you don't want to oversaturate the controls, and that's very natural for me to think about that, right? Because you want to follow a trajectory, then you want to have you don't want to oscillate, back and forth, right? And this is there's a rich tradition of these things in control theory, thinking about hysteresis or dead bands, just to avoid so I'm really, at this point I'm thinking that the particular question is, how did you encode the steering commands for it to arise as a bang-bang control in this case?
So on the bang-bang controller work, we actually didn't evaluate it on a driving task. But what we did do, and where we did observe it, is we literally used the standard, I think it was DeepMind control suite here, the standard policy, the standard benchmark setting of the DeepMind control suite. And there we did not do that many changes to how it is encoded by default in the control suite. So basically, literally in the way they expect the commands, we were providing them. But yeah, I don't remember the details because this was not the part I was working on for this paper. But if you want to know how they exactly were encoded, I think Tim is the person to ask.
Okay, thank you. Oh, there's a question from the chat.
Yes,
Yeah,
so I can read it.
Yeah, go.
Yeah, so there is 2 questions actually regarding the second topic in data-driven simulation. Let's start with the first one. How do you see the difference of this data-driven simulation and data augmentation?
So that's a very good question. And data-driven simulation in some sense is a form of augmentation, but it has a different goal. In classical data augmentation, we just want to increase the amount of training data that is in a somewhat meaningful way. In data-driven simulation, we want to actually have a full feedback loop. So what we want to do is we want to have a form of steerable augmentation, and this allows us to actually train with this feedback loop in the training pipeline. So we can use the feedback loop, for example, as we did in a reinforcement learning agent. The second question was the relationship to NERV and how our data-driven simulator is related to NERV and whether we use a simplified version because we can run in real time. So the first data-driven simulator that you have seen, the Vista work, is no NERV at all. It was also developed before or roughly around the same time as NERV was developed, and it uses only classical reconstruction techniques. We don't perform a full reconstruction of the environment. The only thing that we do is we take our perception stack. If needed, we can reconstruct the depth with some sort of depth estimation, or we use a stereo camera, and that's all the 3D reconstruction we do. I think by now you could almost use NERVs because they had seen so many speed ups recently that they can be run in almost real time. And for simulation, also real time is not as important always because it runs in an offline setting anyway. It's just very desirable for computation speed. But the big challenge for NERVs, which is like one of the big research topics in NERVs now, is to make the things in the NERV editable to allow for manipulation and to allow for composition of different NERV type reconstructions. And in the initial version of our data-driven simulation, there was no NERV at all, but we are, of course, as excited as everyone is about this technology, and we're looking into how they can benefit data-driven simulation approaches.
Okay, the person that asked the question is happy about the answer. Any other question?
Igor, at some point you mentioned the discrete event cameras. I share your excitement about the technology and interest. Now, the one thing that I've been struggling with is finding the a really useful use case where those cameras have definite advantage, right? Were you able to find any, or what are you thinking of?
Yeah, it's a good question. I think the biggest problem that event cameras have is that classical cameras already work so well, and I'm just starting to look more and more into this. I feel the distinct advantage will arise in cases where you would want to avoid classical cameras altogether. For example, if you think about motion estimation of VR headsets, in VR headsets, you don't necessarily need a camera unless you want to visualize something from the VR headset. There, the event camera will give you the benefit of low power, and it will give you the benefit of potential like low latency, because there actually latency and power consumption are somewhat important variables. Although for power consumption, I want to say this very carefully, because the actual power eater in the VR headsets are like, it's usually the display. For driving, I feel it's more the aspect of high dynamic range rather than the aspect of motion blur. So because event cameras have a relatively high dynamic range, it's not as big of a deal if certain parts of an image would be in a classical camera overexposed versus underexposed, so it can deal with it better. But I think it's kind of the general problem of event cameras is that they just improve upon the classical camera, but they except for a few use cases, there is currently no use case where you say they are completely different. So I think that in driving, in flying, like the use cases that Davide is showing, these are, I think, the main use cases where the event cameras have like a very distinct advantage if you want to do flights with very high rotational velocities. Basically, wherever you have motion blur, this is like a very clear advantage yet. In other cases, they have an advantage, but it's basically this advantage can be eaten up by buying just more expensive cameras. But I feel like as things such as power consumption becomes more important in classical driving stacks, and as the event camera algorithms become more and more mature, even the fact that they have small advantages over classical cameras, will create an incentive for people to use them at some point. But yeah, that's a speculation, and I'm curious what you guys think. I mean, you were running at some point, an AV company, and I guess back then it was maybe not mature enough to be used on a car, but I think maybe for the types of tasks for which we use classical cameras on a car, it's interesting why we wouldn't use event cameras once the algorithms are mature enough. Yeah, but I'm curious also to hear what you think from your experience.
Yeah, that's the reason why I'm asking is that because I've been looking for an excuse to use those cameras.
Yeah.
But so that I can go with a straight face and say that this is the best sensor for this particular job. But I've been struggling with that.
Yeah, it has
for some thinking mostly for autonomous vehicles. Okay, so I agree that, for example, for virtual reality and those things that there could be applications.
Yes. And I mean, Davide demonstrated for flight, it is already an amazing sensor. If you have all these
you can demonstrate it that it works, right? But do you have a convincing argument that is much better than something else? So this is so if you had to go to your boss and say, well, we really need to have, to use the event-based cameras for this thing.
Yeah, I think actually the answer to it is maybe no, in a good sense, in a good way, because some of the classical vision algorithms that already exist for classical cameras are still to be developed for event cameras. So if you're building a company, it's maybe not yet there, but as a researcher, you can still do a lot of impactful research by actually building this type of algorithms that will make that will outperform classical algorithms in areas that have not yet been covered by Davide's group.
Okay, fair enough. Okay, thank you, Igor.
All right. Thank you again, Igor, for the great talk. And actually, we wish you good luck for all the next steps.
Yeah, thanks so much for having me. It's been a great pleasure talking to all of you and meeting you. And I hope we will see each other in person again soon.
Yes, hopefully so. Thank you, everyone, and see you next week for the next talk. Bye.
Thank you. Bye.